So let's recall that at the previous lecture we introduced the notion of compact quantum group, and we established a duality of Gelfand-Nymark type between the categories of compact groups and of commutative compact quantum groups. Well, let's recall the definition. By definition, a compact quantum group is a unital C-star by algebra, A with co-multiplication delta, which satisfies the following two density conditions, namely the subspace delta of A multiplied by 1 tensor A. This is a subspace in the tensor product of A by itself, and subspace delta of A multiplied by A tensor 1. So they should be dense in the tensor product. Okay, so let's briefly recall where the definition comes from. First of all, it will start with a compact semigroup. Then we observed that the algebra of continuous functions on this semigroup G is a unital C-star by algebra in a natural way. So the co-multiplication, which acts from A to the minimal tensor product of A by itself, now it acts from C of G to the algebra of continuous functions on G cross G. And this homomorphism corresponds to the multiplication on G. And in fact, we observed by using the Gelfand-Nymark theorem that the category of compact topological semigroups is anti-equivalent to the category of commutative unital C-star by algebras. Now, where the density conditions, where do the density conditions come from? Again, in the commutative case, if A is the algebra of continuous functions on a compact semigroup G, these density conditions mean precisely that our semigroup G is a semigroup with cancellation. And we proved as the previous lecture that a compact semigroup with cancellation is actually a compact group. So as a result, we see that we get an anti-equivalence between the categories of compact groups and of commutative compact quantum groups. So the dual of the category of compact groups is equivalent to the category of commutative compact quantum groups. Okay, so we have the first class of examples of compact quantum groups, namely the algebras of continuous functions on compact groups. So today we discuss much more interesting examples, which are not commutative in general. More exactly, we'll discuss compact matrix quantum groups. And in particular, we'll introduce probably the most famous and the most fundamental example, which was chronologically the first example of a quantum group, namely the quantum SU2 group. The quantum SU2, which was introduced by Voronovich in 1987. Okay, so we start with the following result. We start with a result which serves as a motivation for the definition of the quantum SU2. Namely, I claim that the algebra of continuous functions on the group SU2 is isomorphic to the universal C-star algebra generated by two elements, alpha and gamma, such that the following matrix, alpha, gamma, minus gamma star, alpha star, is unitary. So in other words, we can define the algebra of continuous functions on the SU2 group in terms of generators and relations. Well, let's recall that the group SU2 is defined to be the group of all square 2 by 2 complex matrices G, such that G is unitary, which means that we have the following formula. The G is unitary and the determinant of G is 1. And such matrices can be defined explicitly. They have the following form. They are indexed by pairs of complex numbers, Z and W. Z and W are complex numbers such that they satisfy the following conditions, the following condition. And the matrix GZW has the following form. Well, this is a well-known fact, which is quite easy to check. So in other words, topologically, SU2 is nothing but the sphere, the three-dimensional sphere in the four-dimensional real space. Okay, now we introduce the elements alpha and gamma. So basically what we want to do, we want to find two elements alpha and gamma in the algebra of continuous functions on SU2, such that the respective matrix, this matrix is unitary, and such that the suitable universal property holds. That is, for any other unital C-star algebra with two elements satisfying the same condition, there is a unique homomorphism from this algebra of continuous functions on SU2 to our C-star algebra A. So first we have to construct alpha and gamma. We define alpha and gamma. They are continuous functions on SU2. As follows. So alpha and gamma are just coordinate functions. Alpha takes the matrix to the upper left corner, and similarly gamma takes G to W. Okay, so we can form the respective matrix. So U will be matrix alpha, gamma, minus gamma star, and alpha star. So this is a 2 by 2 matrix over the algebra of continuous functions on SU2. And to show that this metric is unitary, let's observe that this algebra is naturally identified with the algebra of continuous functions on SU2 with values in 2x2 matrices. So a scalar matrix of continuous functions is the same thing as a continuous functions with matrix entries. Okay, and under this correspondence, the matrix U corresponds exactly to the inclusion map of SU2 into M2. This already implies that U is unitary because the product, the multiplication, and the involution on this algebra of continuous functions are defined pointwise. And so a continuous matrix valued function is unitary if and only if its range is contained in unitary matrices. But the inclusion map obviously satisfies this condition. And so this observation implies that U is unitary. Okay, so now we have to check the universal property. Suppose now that we have a unital C-star algebra A. Suppose that A is a unital C-star algebra. And suppose we have two elements, A and B. Such that the following matrix, let's denote it by V. It is the matrix AB minus B star A star. Suppose that this matrix is unitary. The following elementary exercise. This matrix V is unitary. So explicitly, this can be written as follows. This means exactly that, first of all, the elements A, B, A star, and B star commute. And moreover, A star A plus B star B is 1. This is an easy exercise, which is quite straightforward. Okay, so in particular, this exercise implies that if we take the C-star subalgebra, let's denote it by B, let's denote by B the C-star subalgebra A generated by little a and little b. So,
excuse me, am I correct that if we say that V is unitary, it means precisely that V star with a T is equal to V?
No, unitary means that V star equals 1 and V star V equals 1.
Sorry.
Let me write this down. This means that V star V equals V star equals 1. This is the definition of a unitary element. So these two, when we write this down explicitly, calculate the product of matrices, we see that this is equivalent to the following conditions on A and B. Okay, so if we now take the C-star subalgebra A generated by little a and little b, then the above exercise implies that B is commutative. B is commutative. Okay, now let's denote by X the maximal spectrum of B. We take any element in the maximal spectrum. Let's denote it by chi. So we identify the spectrum with the character space. So chi is a unital character of A, and we apply chi to this formula. So when we apply chi to this formula, we get the following: chi of A squared plus chi of b squared is 1. So in other words, the pair chi of a and chi of b sits on the sphere in C2. So we get a map. Let's denote it by f. Let's consider the following map: f from x to SU2, which takes each character chi to the matrix corresponding to the pair chi of a and chi of b. So this is the explicit form of our matrix. We substitute chi of a here and chi of b here. And this will be matrix in SU2. And it's more or less clear that this map is continuous. So we can consider the induced map, f dot, which acts from the algebra of continuous functions on SU2 to the algebra of continuous functions on X. This is the homomorphism induced by f dot. Now X is the maximal spectrum of B, and by the Gelfand-Nyberg theorem, B is the Gelfand transform is an isomorphism of B onto C of X. So we compose this. We can compose this with the inverse of the Gelfand transform. So this is isomorphic to B, and B is contained in A. So when we take the composition of these maps, we get a star homomorphism phi from the algebra of continuous functions on SU2 to A. And it easily follows from the construction. This is a little exercise for you, which is quite straightforward, that phi is exactly what we're looking for. So phi takes alpha to A and gamma to B. Okay, so we have almost proved the universal property of our algebra. To complete the proof, we have to prove that such a homomorphism is unique. Well, the uniqueness of phi is a simple application of the Stone-Weierstrass theorem. Well, indeed, by the Stone-Weierstrass theorem, if we take the star subalgebra of the algebra of continuous functions on SU2, generated by alpha and gamma, so it clearly separates the points of SU2, and so it is dense by the Stone-Weierstrass theorem. And this completes the proof. So this shows that a homomorphism phi, which takes alpha to A and gamma to B, is unique.
Am I right that in this proof, we just used the topological structure of SU2 and we didn't use its group structure?
Yes, exactly. At this point, we didn't consider the co-multiplication on this algebra of continuous function on SU2. So at this point, we forgot about this, and we considered only the underlying topological space, that is the three-dimensional sphere. The co-multiplication will appear when we discuss the quantum version of this algebra. Okay, so now we can use this formula as a motivation, and we introduce the quantum SU2 group. So suppose that Q is a real number between -1 and 1 and different from 0. We define the algebra of continuous functions on the quantum SU2, algebra of continuous functions on the quantum SU2, or briefly just the quantum SU2. So we define this algebra as follows. This is a sister algebra, which will be denoted like this. Or another notation is SUQ of 2. And by definition, this is the universal sister algebra generated by two elements alpha and gamma, such that the following matrix, alpha gamma minus Q gamma star alpha star, is unitary. Of course, let me put the quotation marks here. Of course, this is not an algebra of continuous functions on any space because it is not commutative. But according to the philosophy of non-commutative geometry, we know that it is very useful to consider non-commutative sister algebras, non-commutative unital sister algebras as algebras of continuous functions on quantum spaces. So in some sense, according to this philosophy, this algebra may be interpreted as the algebra of continuous functions on the respective quantum groups, on the respective quantum group. Okay, so it's clear from this definition and from the previous proposition that if Q equals 1, then we get exactly the algebra of continuous functions on SU2. So this follows from the previous proposition. In some sense, the family of these algebras indexed by number Q can be interpreted as a continuous deformation of the algebra of continuous functions on SU2. And this statement can be made precise if we use the language of continuous bundles or continuous fields of sister algebras. But this is a long story, which is quite different from our main topic. So, so this is outside the scope of our course. So anyway, in some informal sense, this is kind of a deformation of the algebra of continuous functions on the SU2 on the SU2 group. Okay, so at this point, this is just a unital sister algebra. So what we want to do is to make it into a compact quantum group. So to make it into a compact quantum group, we must introduce the co-multiplication, which is rather easy. And we have to show that our density conditions are satisfied. And this is not so easy. So we'll prove this fact in the more general setting of compact matrix quantum groups. So let's now introduce some notation. Suppose that A is star algebra, Should it be unital? Well, not necessarily A, just in star algebra. And suppose that U is a square n by n matrix over A. We define two matrices, U transpose and U bar, as follows. U transpose is just the usual transpose matrix. In the usual sense. And U bar is the matrix which is obtained by taking the joints of the matrix entries. So U bar ij is Uij star. And let's also observe that the joint of U star, is nothing but U bar transpose. Exactly as in the case where A is the field of complex numbers. Okay, now we give the following definition. A compact matrix quantum group is a triple A, delta, and U, where A is a unit of sister algebra, delta is a unit of star homomorphism from A to tensor product, A tensor A. Is a unit of star homomorphism. And U is a square n by n matrix over A, such that the following conditions are satisfied. First of all, both U and U transpose are invertible. Condition 2, A is generated by the matrix entries of U. A is generated by the elements Uij. I mean, generated as a C-star algebra, as a unit of C-star algebra. And finally, condition 3, if we apply delta to each matrix entry, Uij, then we get the following sum, Uik, Ukj over k for each ing. Okay, so this is the general definition of a compact matrix quantum group, which, by the way,
that it's a bialgebra.
Yeah, but this is not immediate. We will prove this in 10 to 15 minutes. So in the definition, we don't require that delta is co-associative. Okay, so this definition is also due to Voronovich, but it was given earlier than the general definition of a compact quantum group. Namely, in 1991. More exactly, the original definition was given in 1987, but it was equivalent, but it was different from this one, and it was much more complicated. So the simplified definition, which is equivalent to the original one, was given by Voronovich in 1991. By the way, let's observe we can slightly modify this definition. We observe that U transpose is invertible, if and only if U bar is invertible. The reason is that these two matrices are adjoint to each other. The adjoint of U transpose is just U bar. Okay, let's look at an example, which is in fact a motivation for the definition. Suppose that we have a closed subgroup in the unitary group. G is a closed subgroup in U of n. And let A be the algebra of continuous functions on G. So we define a matrix U as follows. Uij is just the coordinate function. Uij takes each matrix G to the respective matrix entry, Gij. So again, as in our first example of today's lecture, we identify Mn of A with the algebra of continuous functions from G to the matrix algebra Mn. And under this correspondence, U corresponds to the inclusion map of G into Mn. So it is unitary. It is unitary, and in particular, we see that for each G in G, little g in our group, the matrix U of G and the matrix U of G transpose are invertible. Simply because U of G is unitary. And this means exactly that U and U transpose are invertible. So our first condition from the definition of compact metric quantum group is satisfied. Condition 2 is generated by the matrix entries, follows from the Stone-Weierstrass theorem. Stone-Weierstrass theorem implies that condition 2 holds. And to prove condition 3, we do a simple calculation. So what is delta of Uij? This is a function. So we identify the algebra of continuous, the tensor product of C of G by C of G with the algebra of continuous functions on the product G cross G. So this is a continuous function on the product. And it follows from the definition of the co-multiplication that this is just Uij evaluated at the product GH. Well, this is just the ijth entry of the product of two matrices. So by the well-known rule of matrix multiplication, this is the following sum, Gik Hk J. Or currently, we can write this as follows. We consider the following element in the tensor product, Uik tensor Ukj, and evaluate it at G and H. Okay, so we see that condition 3, that is this element is equal to this element. Condition 3 holds. And so we conclude that C of G, together with this matrix U, and with the canonical co-multiplication, is a compact matrix quantum group. Is a compact matrix quantum group. So this is the motivating example. In fact, it turns out that each commutative compact matrix quantum group arises in this way. But at this point, we cannot prove this fact. The key point here is that if we take any compact matrix quantum group, then the respective fundamental matrix U, which is a part of the definition, can be chosen in such a way that it is unitary. This is true, but this is not obvious. Probably we will be able to prove this in maybe 2 to 3 lectures. Okay. So anyway, now initial question is it true that any compact matrix quantum group is a compact quantum group? And of course, the answer is yes. So we have the following theorem. If A delta and U is a compact matrix quantum group, then A with the same co-multiplication is a compact quantum group. Okay, so first of all, we start with a simple exercise, which is a part of the proof. So the co-associativity of the co-multiplication easily follows from axiom 3. So this formula, together with the assumption that A is generated by Uij, modulo some little calculation, shows that delta is co-associative. So axioms 2 and 3 imply that delta is co-associative. Okay, now we have to prove the density conditions, which is the most interesting part of the proof. Well, let's use the following trick. Let's introduce the following subspace, let's denote by B, the set of those elements in our algebra A, such that A tensor 1 belongs to delta of A multiplied by 1 tensor A. So clearly this is a vector subspace in A, which contains the identity. I claim that B is actually a unital subalgebra. This is lemma 1. B is a unital subalgebra. Oh, wait. Well, let's show that this is indeed the case. So suppose that A and prime are two elements in B. So by definition, we can write A tensor 1 as the following sum, the finite sum, delta of Bj, 1 tensor Cj, finite sum over J. And similarly, we can write A prime tensor 1 in a similar way. So the finite sum over K, delta of Bk prime, or 1 tensor Ck prime. So we now take the product a prime, consider the following element. So what is this? So this is the product of a tensor 1 and a prime tensor 1. And by assumption, so a tensor 1 has the following form. So we just substitute this formula here. This is the sum over j, delta of bj. And we can write this as follows. This is delta of bj multiplied by a prime tensor 1 and by 1 tensor cj. So here we use the simple fact that these two elements, this one and this one, obviously commute. Okay, now we again take a prime tensor 1 and substitute it here. So we get the following double sum over j and k, delta of bj, delta of bk prime, 1 tensor ck prime, 1 tensor cj. And finally, since delta is a unital morphism, this can be written as follows: the sum over j and k, delta of bj bk prime multiplied by 1 tensor ck prime cj. And the resulting element obviously belongs to this subspace. And so this implies that AA prime, the product AA prime, sits on B. So this completes the proof of lemma 1. Lemma 2. Lemma 2, I claim that each matrix entry Uij belongs to B for each I and j. Here U is the same fundamental matrix which appears in the definition of a compact matrix quantum group. To prove this result, we recall that U is invertible and let V denote the inverse of U. So we let's look now at the following element: the sum over j, delta of sum over k, delta of uik multiplied by 1 tensor vkj. So clearly, this element sits in our subspace, in this subspace. But on the other hand, we can write this element as follows. So delta of uik by assumption is the sum over L, so we get double sum over k and L. And delta of uik will be the sum over L, ulk. And we must multiply this on the right by vkj. Okay, now since U and V are inverses to each other, we see that after we take the sum over k of this expression, we get the Kronecker delta Lj, and as a result, the whole sum will be equal to Uij tensor 1, Uij tensor 1. And if you now recall the definition of our subalgebra B, we see that Uij sits in B. Because the left-hand side of this identity, I mean this expression, is obviously in B. A similar argument shows that the following is true, lemma 3. Uij star sits in B for each ing. The proof was similar to lemma 2. We just use the assumption that the matrix U transpose, or equivalent the matrix U bar, is invertible. Okay, and now the end of the proof of our theorem. Well, since A is by assumption A is generated by the elements Uij as a C-star algebra, so lemmas 2 and 3 imply that B is dense in A. B is dense in A. If we now take an arbitrary element B in our subalgebra B and an arbitrary element A in A, we see that the element B tensor A can be written as follows. Little b, first of all, this is a product, B tensor 1, 1 tensor A. And B tensor 1 belongs to delta of A multiplied by 1 tensor A by assumption. And the second element here, 1 tensor A, also sits in 1 tensor A. And so obviously we have the following equality, which implies that the algebraic tensor product of B and A is contained in delta of A 1 tensor A. Okay, but we already know that B is dense in A. And so this algebraic tensor product is dense in the C-star tensor product of A by itself. And since this space is bigger, we conclude that it is also dense. And this is our first density condition. And the second density condition is proved similarly. A similar argument shows that delta of A multiplied by A tensor 1 is dense in the tensor product. This is a little exercise, which is very easy. And this completes the proof. So we see that each compact matrix quantum group is a compact quantum group. Okay, let's now come back to the quantum SU2 group, and let's show that it is a compact matrix quantum group. So as a result, we will see that it is a compact quantum group. So we have the following proposition. So as before, we suppose that Q is a real number between -1 and 1 and different from 0. And let U be the unitary matrix which appears in the definition of the quantum SU2. Alpha, gamma, minus gamma star, alpha star. Well, first of all, I claim that the defining relations for our algebra CQ over SU2, namely the relation that the matrix U is unitary, are as follows. Alpha gamma equals Q gamma alpha. Alpha gamma star equals Q gamma star alpha. So in this case, we say that alpha and gamma are Q commuting, and similarly, alpha and gamma star are Q commuting. Next, gamma is normal. Gamma is normal. One more relation is similar to the commutative case. Alpha star alpha plus gamma star gamma is 1. And finally, we have one more condition, which is kind of quantum unimodularity condition. In some sense, the quantum determinant of U is 1. More exactly, alpha alpha star plus Q squared gamma star gamma is 1.
Now we're just rewriting the condition that you use unitary, right?
Yeah, exactly. If you explicitly write the condition that U is unitary, you get precisely these relations. This is just a little elementary calculation. We have already discussed this in the in the commutative case where Q is 1, and in the general case, the relations are as follows. So this is just equivalent to the assumption that U is unitary.
And the stars. Okay, yeah, I get that. Yeah, thank you.
Okay, so this is the first part of the proposition. Now the second part. There exists a unique unit of star homomorphism, delta from our algebra to its tensor square. Such that delta satisfies the respective condition in the definition of a compact matrix quantum group. There's delta of Uij, delta of Uij is the sum over K from 1 to 2 Uik Ukj. So explicitly, this means that delta of alpha is, so this is U, so delta of alpha is alpha tensor alpha minus Q gamma star gamma. And delta of gamma is gamma tensor alpha plus alpha star tensor gamma. So it's enough to consider only alpha and gamma, because since delta is a star homomorphism, we automatically get respective formulas for delta of alpha star and delta of gamma star. Okay, and part 3, which is the main part of this proposition, our algebra, quantum SU2, together with delta and U, is a compact matrix quantum group. So as a corollary, it is a quantum. It is a compact quantum group. Well, the proof Parts 1 and 2 are simple exercises. Part 1 is a straightforward calculation. So you just write the condition that you use unitary, and what you get are as a result you get exactly these relations between alpha and gamma. Condition 2 follows from the universal property of the quantum SU2 group. So we defined this algebra as the universal unitary C-star algebra generated by alpha and gamma with the respective condition. So to show that the existence and the uniqueness of such homomorphism, we just define delta formally on the matrix entries, and we check explicitly that the resulting 2x2 matrix, which consists of this element, and the other two elements, it is unitary in the tensor square over the tensor square of this algebra. And then we just apply the universal property of this algebra. Again, this is an elementary calculation. Well, and now to prove part 3, it suffices to show that U bar is invertible, because U is unitary, and the unitary matrix is also invertible. So why is U bar invertible? This is a little trick. So we take a complex number lambda, which is a square root of Q. Square root of Q. Then a little calculation shows the following formula. If we take U transpose and multiply it on the left by this matrix, on the right by this one, what we get is exactly U bar. Well, I had to check my notes because it's easy to make a mistake here. I don't remember exactly if this is correct. Maybe I should put the minus sign into the different place. Okay, this is correct.
I'm sorry.
Oh, this is not. No, this is not correct. Sorry, not U transpose, but this should be U bar, and this is U. Okay, so we already know that U is invertible, and this formula easily implies that U bar is also invertible.
Sorry, but how can it be that U is not invertible? U is invertible and U bar is not invertible? Because if U is invertible, that means that there exists some W, that W is 1, and then U bar, W bar is 1 bar, and I believe that 1 bar has to be 1.
A delicate point is that the operation of which takes U to U bar is not multiplicative unless we assume that the algebra is commutative. If the algebra is commutative, then this is correct. This operation is multiplicative. But if our algebra is not commutative, then this operation is not.
Still, if U W is 1, then U W bar is, I believe, W bar U bar. No,
this is not correct. This is true if our algebra is commutative. But if you try to write this down explicitly.
I get it. Thank you.
If you try to write this down explicitly, you will see that unless we assume that the algebra is commutative, we cannot prove that U V bar is U bar V bar, and so we must require explicitly that the U bar is also invertible. And the assumption that it is invertible was essentially used in our proof that compact matrix quantum group is a compact quantum group. It was our lemma 3. So when we proved lemma 3, we used the assumption that U bar is invertible. Okay. So anyway, I hope this formula is correct. You can easily check this. And obviously, this formula implies that U bar is also invertible. Okay, so the quantum SU2 is indeed a compact quantum group. It's interesting to compare the quantum SU2 group with a pure algebraic object, namely the quantum SL2 group. The quantum SL2 and the quantum SU2. Okay, let's start with the classical situation, with the commutative situation. So we take the complex SL2, SL2C. So by definition, this is the group of all unimodular square 2x2 matrices. Of those G, or matrices 2x2 matrices G, such that the determinant of G is 1. And let's look at the following map. Let's denote by sigma, the map from SL2 to itself, which is given by the following formula. Sigma of G is G G bar transpose and inverse. So by using this map, we easily observe that SU2 is nothing but the set of fixed points of this map sigma, set of all G and SL2, such that sigma of G equals G. Also, sigma is not just a map. Actually, sigma is a group automorphism of SL2. Moreover, it's an involution in the sense that sigma squared is the identity map. And also, it is, if we take the differential at the identity, the resulting map is, well, clearly it is linear over the real numbers, but it is antilinear over the complex numbers. It's complex antilinear.
What's the delta sigma?
The differential. So, well, sigma is a smooth map from. It's a smooth map of a smooth manifold on itself. We can take the differential at the identity, and this map is antilinear. Antilinear. So the last two properties, I mean, this line and this line, together mean that SU2 is a real form. SU2 is a real form of SL2. Okay, let's now look at the algebra of, so first of all, SL2 is of course an affine algebraic variety. It's a variety in the 2x2 matrices. So let's now look at the algebra of regular functions on SL2. Script O of SL2 is the algebra of regular functions on SL2. And this algebra can be written as the quotient or the algebra of regular functions on the 2x2 matrices, modulo the ideal generated by the determinant -1. And even more explicitly, what is this? Well, the algebra of regular functions on M2. M2 is a vector space, so this is just the polynomial algebra in 4 variables, A, B, C, and D. And the determinant is AD minus BC. So this is the explicit representation of the explicit description of the algebra of functions of regular functions on the SL2, on the group SL2. Let's now observe that this algebra has an involution. Involution on this algebra can be defined by the following formula. If f is a regular function, then we define f star of g to be the complex conjugate of f of sigma of g. And it's easy to see that this is indeed an involution. So the algebra of regular functions becomes a unital star algebra. By the way, we can now reconstruct both SU2 and SL2 from this algebra. The following simple exercise. SL2 is nothing but the set of all unital characters. There is a one-to-one correspondence between SL2 and the set of all unital characters of this algebra. And the correspondence is more or less obvious. We just take any point in SL2 and consider the respective evaluation character. And under this correspondence, SU2 corresponds precisely to the set of all unital star characters. Unital star characters of the same algebra. So our star algebra of regular functions keeps all information about SL2 and about SU2. Okay. Now, a natural question is how to reconstruct the algebra of continuous functions on SU2 from the algebra of regular functions on SL2. And the answer is very easy. Let's introduce the following map. Let R denote map from the map from the algebra of regular functions on SL2 to the algebra of continuous functions on SU2. It's just the restriction map. Each regular function is continuous, so we just restrict f to SU2, and we get R. And we have the following simple exercise. The algebra of continuous functions on SU2, together with this map R, which is clearly a star homomorphism, is a sister envelope of the algebra of regular functions on SL2. So in summary, we see that to get SU2 from SL2, we need two steps. First, we need to define an involution on the algebra of regular functions. And the second step is to take the C-star envelope. Well, basically, this exercise is equivalent to our first proposition of today's lecture, which gave us the universal property of the continuous function on SU2. Okay, by the way, one more exercise, which is elementary, but it will explain later the quantum case, the involution on our algebra of regular functions is uniquely determined by the following formula. A star equals D and B star equals minus C. Basically, this is equivalent to the well-known formula for inversion of 2x2 unimodular matrices. Okay, so this was the motivation. So far, we discussed the commutative situation. Now let's look at the quantum analog. So we give the following definition. Suppose that Q is a non-zero complex number. We define the algebra of regular functions in quotation marks on the quantum SL2 group, on the quantum SL2 as follows. So this is the unital algebra denoted like this, generated by 4 elements. A, B, C, and D, like the algebra of regular functions on SL2, that is generated by 4 elements. But this algebra is no longer commutative, and the commutation relations for these 4 elements are as follows, with the following relations. A and B are Q commuting. AB equals QBA. AC equals QCA. AB CD equals QDC. Similarly for B and D, BD equals QDB. Now the elements B and D commute. Oh, sorry, B and C. B and C commute. Now A and D, AD minus DA is Q minus Q inverse BC. And finally, the quantum determinant, AD minus QDA is 1. And this element is called the quantum determinant. Okay, so quite strange relation at the first glance, but what is clear from the definition that if Q is 1, we observe that if Q is 1, then our algebra of regular functions on the quantum SL2 is exactly the algebra of regular function on SL2. Because in this case, all these relations mean exactly that A, B, C, and D commute, and that the determinant is 1. I'll explain in a few minutes where these strange relations come from. And now let's discuss relation.
I hate to be the alarm clock, but I'll just remind that now.
Yes, yeah, true. Well, if you don't mind, I'll just explain relation with quantum SU2, and then we finish. So we have the following exercise. First of all, suppose that Q is real. Let's suppose that Q is a real number. And of course, non-zero real number. Part 1, there is an involution on the algebra of regular functions on the quantum SL2, uniquely determined by the following formula. A star equals D, and B star equals minus QC. So let's compare this with the above involution on the non-quantum algebra of functions on the SL2 group. So the difference is that we put Q here. Now exercise 2. Suppose now that Q is between -1 and 1, so that the quantum SU2 group is defined. Then there is a unique star homomorphism from the algebra of regular functions on the quantum SL2 to the algebra of continuous functions on the quantum SU2, which takes A to alpha and C to gamma. And finally, the quantum SU2 group, together with this homomorphism R, is a C-star envelope of the algebra of regular functions on the quantum SL2. So this is an exact quantum analog of the above classical situation. The exercise is actually very easy, because if you write down the commutation relations between alpha and gamma once again, you'll see that basically these relations are essentially equivalent to the above commutation relations between alpha, between A, B, C, and D from the previous definition. So this exercise is essentially equivalent just to the definition of the quantum SU2 group. And finally, well, just a few words about where these strange relations come from. Actually, there are several independent sources for such relations. First, they were introduced by Fadeev and Takhtajan in 1986. And for them, the motivation was purely, the motivation came from physics. They studied the so-called quantum Liouville model. And somehow they deduced from some physical motivations these relations. About the same time, the same relations were independently discovered by Drinfeld and by Waxman and Soibelman. For them, the starting point was in some sense dual. They started with the so-called quantized enveloping algebra of the Lie algebra SL2. This was the initial object for them. So they constructed the algebra of matrix coefficients of finite dimensional representations of this quantized enveloping algebra. And they proved that the defining relations for this algebra of matrix coefficients look exactly as here, as in this definition. About the same time, Voronovich defined his quantum SU2 group, which is defined by essentially the same relations. And his motivation was mathematical. He studied the so-called twisted unimodularity condition. And perhaps the most elegant explanation, the most elegant approach to these relations, was found by Manin in 1987. He followed the general philosophy that quantum group should act on quantum spaces, like in the same way like groups act on spaces. Quantum group should act, or more exactly, co-act on quantum spaces. So Manin considered the so-called quantum plane, which is a very fundamental algebra, and it is defined as algebra. This algebra is defined by two relations, x and y, two generators, and one relation, xy equals q, yx. So he called this algebra the quantum plane. And by using the requirement that the quantum SL2 should coact on this algebra, he deduced all these commutation relations. Probably this is the most natural explanation. So these relations can be deduced from the requirement that the quantum SL2 group should coact on the quantum plane. Okay, so that's all for today. At the next lecture, we maybe briefly discuss some more examples of compact quantum groups, the so-called free quantum groups. And next, the main goal of the next lecture will be to construct the so-called higher state on an arbitrary compact quantum group. So the higher state is a natural non-commutative analog of the higher measure on a compact group. Okay, thank you.
Спасибо. До свидания.
Спасибо. До свидания.